In the Relativity 106 videos, we're going to introduce tensors. Tensors are mathematical tools that are important for studying relativity because they help us write the laws of physics in a way that's the same in all coordinate systems. In this video, we'll start by introducing covectors, which are a very important type of tensor, just like vectors, and then we'll apply covectors to the Doppler effect in relativity. In future videos, we'll give the definition of a tensor and talk about the tensor product. So in relativity, a vector is basically like an arrow, and a vector is used to represent something with a direction and a size. Meanwhile, a covector is basically like a stack, and it represents something with a direction and a density. We've already seen how vector arrows can give us geometrical representations of position, velocity, acceleration, momentum, and force, in both 3D space and 4D spacetime. In this video, we'll see that covectors can give us a geometrical representation of waves, which basically have a density in time called frequency and a density in space called the wave number. This will help us give a geometrical interpretation of the Doppler effect. So in the first part of this video, we're going to discuss covectors from the point of view of pure mathematics. Then we'll apply this to the Doppler effect in Galilean relativity, then special relativity in inertial frames, and then special relativity in non-inertial frames. I cover covectors more slowly in my Tensors for Beginners videos 4, 5, and 6, so you can check the description for links to those videos. If you already understand covectors, you can skip ahead to this part of the video and go straight to the Doppler effect. So a covector is an oriented stack that eats a vector as input and then outputs a number. So here is a covector stack in 2D oriented in this direction. And here is a covector in 3D oriented in this direction. So let's say that we have a vector called v and a covector called alpha. When alpha takes v as input, this outputs alpha of v, which is just the number of stacks pierced by the vector v when we lay it over top of the covector alpha. So if we look here, the vector v pierces 1, 2, 3 stacks of alpha. So alpha of v is equal to 3. In this example, v pierces 1, 2 stacks of alpha, so alpha of v is equal to 2. In this example, v pierces one stack line, but gets halfway to the second stack line, so we say that alpha of v is equal to 1.5. So the result of alpha of v is non-integer if the arrow makes it part way between the stacks. Over here, v pierces 1, 2 stacks of alpha, but this is pointing in the opposite direction of alpha's orientation, given by these arrows. So we say that alpha of v is -2 instead of +2. So the result of alpha of v can be negative if the vector arrow points in the direction opposite of the stack. And finally, here the vector v doesn't pierce any stacks at all, so alpha of v is equal to 0. So the result of alpha of v can be 0 if the vector arrow is parallel to the stack lines. Now let's study some of the properties of covectors. With this covector alpha and this vector v, we see that v pierces 7 stack lines, so alpha of v is equal to 7. And in the case of the vector u pierces 3 stack lines, so alpha of u equals 3. And w pierces 4 stack lines, so alpha of w equals 4. Now notice that these 3 vectors form a triangle, and they obey the equation v equals u plus w. Notice that it's also true that alpha of v, which is 7, equals alpha of u, which is 3, plus alpha of w, which is 4. So this is our first geometrical property of covector stacks. When alpha acts on a sum of vectors, alpha of u plus w, this is equal to the sum of alpha acting on the individual vectors, alpha of u plus alpha of w. So when it comes to a covector acting on a sum of vectors, we can either add the inputs or add the outputs, and we'll get the same result. Now in this example, v pierces 3 stack lines, so alpha of v equals 3. Now watch what happens if we double the length of v to get 2v. The vector 2v pierces 6 stack lines, so alpha of 2v equals 6. Notice that when we double the length of the input vector, this is the same thing as doubling the output of alpha acting on the original vector. So this is another property of covectors. We can either scale the input vector or scale the output by the same scalar n, and we'll get the same results. So these two properties are the fundamental laws of covectors. We can either add the inputs or add the outputs of covectors and get the same results. And we can either scale the inputs or scale the outputs of covectors and get the same results. When we apply these two properties together, when we have alpha acting on a linear combination, AU plus BW, we can split alpha to each term in the sum and then bring these scalars outside to get A alpha of U plus B alpha of W. So for covectors, we can either do linear combinations of inputs or linear combinations of outputs with the same scaling constants, and we'll get the same results. This is a very useful fact because if we have alpha of v and then we expand v as a linear combination of a basis ex and ey with components vx and vy, we can split alpha across the two sum terms and then bring the vector components outside. So if we want to know how alpha acts on an arbitrary vector v, all we really need to know is how alpha acts on the basis vectors ex and ey. If we know how alpha acts on a basis ex, ey, then we know how it acts on any vector v. We call alpha of ex and alpha of ey the components of alpha in the ex, ey basis, and we write them as alpha x and alpha y with subscripts. Now, something we've learned in past videos is that vector components are contravariant. If we have a vector v measured in the basis ex, ey, we see that v is equal to 1 copy of ex plus 1 copy of ey. Now, if we change the basis vectors to make them twice as big and get ex tilde, ey tilde, then we can write the same vector v as 1/2 ex tilde plus 1/2 ey tilde. When the basis vectors get twice as big, the components of v get twice as small and become 1/2, 1/2. Vector components will always change in the opposite way that basis vectors do, so we call vector components contravariant. Now let's look at what happens to covector components when we change basis. So looking at this covector alpha, when we measure its components using the ex and ey basis vectors, we see that ex pierces 2 stack lines, so alpha of ex, or alpha x, is 2, and ey also pierces 2 stack lines, so alpha of ey, or alpha y, also equals 2. Now again, let's double the length of the basis vectors to get ex tilde and ey tilde. Now ex tilde pierces 4 stacks, so alpha of ex tilde, or alpha x tilde, is equal to 4. And ey tilde also pierces 4 stacks, so alpha of ey tilde, or alpha y tilde, is also equal to 4. Notice that when we doubled the length of the basis vectors, the size of the covector components also doubled. This means that covector components are covariant, because they change in the same way that basis vectors do. If the basis vectors become twice as big, then covector components will also become twice as big. So given that we build vectors using basis vectors, scaled and added in linear combination, you might wonder if there's a basis for covectors as well. And it turns out that there is. We call a basis for covectors the dual basis, and we write it using the Greek letter epsilon. The dual basis vector epsilon x is defined in such a way that when it acts on ex, we get 1, And when it acts on any other basis vector in the same basis, we get 0. So this means that the covector epsilon x looks like this. Ex pierces one stack line and Ey doesn't pierce any stack lines. Similarly, the basis covector epsilon y is defined so that when it acts on Ey, we get 1, and when it acts on any other basis vector, we get 0. So epsilon y looks like this. Ey pierces one stack line and Ex pierces no stack lines. When basis covectors are taken in linear combination, the rule for addition is to add the densities together. So if we have 2 epsilon x plus 1 epsilon y, what this is saying is that the resulting covector will have a density in the x direction of 2 and a density in the y direction of 1. So this resulting covector alpha has the Ex basis vector pierce 2 stacks and has the Ey basis vector pierce 1 stack. So its density in the x direction is 2, and its density in the y direction is 1. We can confirm this algebraically by having alpha act on the Ex basis vector. So alpha is really 2 epsilon x plus 1 epsilon y, and we can pass the input Ex to each of these basis covectors. Epsilon x of Ex is 1 by definition, and epsilon y of Ex is 0. So we get that the density in the x direction is 2 as expected. And following a similar process for Ey, we get that the density in the Ey direction is 1 as expected. It turns out that the epsilon basis covectors are contravariant. The epsilon x basis covector that is dual to the basis vector Ex satisfies these properties. When we double the length of the Ex-Ey basis to get Ex tilde Ey tilde, the new dual basis covector epsilon x tilde must now satisfy these properties, where Ex tilde pierces it once and Ey tilde doesn't pierce it at all. To do this, epsilon x tilde must become half as dense as epsilon x. The same is true for epsilon y tilde. Since the epsilons transform in the opposite way that basis vectors do, we call them contravariant. It makes sense that covector components are covariant, written in a row, and basis covectors are contravariant, written with a column. We can transform the components with one matrix and then transform the basis with the inverse matrix, leaving the covector invariant. So to summarize covectors from a pure mathematics point of view, covectors are like stacks. They eat vector inputs and output numbers. The output of alpha of v is the number of stacks pierced by the vector v. And the two fundamental covector laws tell us that we can either add inputs or add outputs and get the same result, and we can scale inputs or scale outputs and get the same result. Also, for any vector basis Ex and Ey, covectors have a dual basis given by epsilon x and epsilon y, and the dual basis is defined such that when an epsilon basis covector acts on its partner basis vector, we get 1, and if it acts on any other basis vector, we get 0. Also, the components of a covector are given by counting how many stack lines are pierced by the basis vectors. Also note that basis vectors and covector components change in the same way, which means covector components are covariant. But basis vectors and basis covectors change in opposite ways, so basis covectors are contravariant. And one last thing, if vectors live in a vector space V, we say their partner covectors live in the vector space V star, called the dual space. Now let's look at a practical application of covectors in physics, which is understanding the Doppler effect, in both the relativistic and non-relativistic cases. First, let's look at the properties of waves. Let's say that we have a wave like this that's traveling through space in the positive x direction. Let's say that we take a photograph of the wave so that it is frozen in time, and we can look at how the wave changes over space in the x direction. We say that the distance between wave peaks in the x direction is called the x wavelength, and we denote it by lambda x. We can also count the number of wave peaks per unit distance in the x direction, and we call this the linear wave number, denoted by kappa x, and it is equal to the reciprocal of the wavelength. There is also the angular wave number k, which is 2 pi times the linear wave number, but we will not be using the angular wave number very much in this video. Let's again look at our traveling wave, but instead let's focus on the wave at a single point of constant x over time. We can see that at our point of constant position, the wave makes a periodic up and down motion. So we can also look at how a wave changes over time at a specific position. The time between wave peaks at a constant position is called the period, denoted by capital T. We can also count the number of wave peaks per unit time, and we call this the linear frequency, denoted by f. And this is equal to the reciprocal of the period. There is also the angular frequency omega, which is 2 pi times the linear frequency. But again, we won't be using the angular frequency very much in this video. Technically speaking, the y and z directions also have their own wave numbers, but I'm going to assume they are 0 for this video and just focus on a wave traveling in the x direction. So our wave is changing in both space and time, and it can be tricky to visualize this. The easiest way to visualize a wave is on a space-time diagram. If we have a wave that's moving to the left, we can take a photograph of the wave at each second, and arrange all these photographs together in a space-time diagram to get a 2D visualization of the wave. We can now see how the wave is changing in both time and space. We know that this wave is moving to the left, since if we follow any peak on the wave, we see that it is traveling left as we move into the future. The speed of the wave is given by how much distance one of these peaks covers in a unit of time, and it is equal to the frequency divided by the wave number. This has units of distance over time, which is what we expect for speed. We can simplify this diagram just by drawing lines that represent wave peaks. But we can still see that the wave is traveling left, and we can still see how often it changes in time and space. So our wave can be drawn on a space-time diagram as a stack, or a covector. We call this the wave covector, or sometimes the frequency wave number covector. We denote this wave covector by the Greek letter kappa without any subscripts. We can use the wave covector to understand the Doppler effect geometrically. The Doppler effect basically says that when we run towards the source of a wave, its frequency gets higher, and if we run away from the source of the wave, its frequency gets lower. Let's say that we have a stationary sound wave generator that is producing a wave that moves to the left. Einstein is also stationary, positioned some distance away. To measure this wave covector, all we have to do is use Einstein's spacetime basis vectors ET and EX. The wave's frequency is just its density in time, which is just the wave covector kappa acting on the time basis vector ET. And the wave's wave number is just its density in space, which is just the wave covector kappa acting on the EX basis vector. We see that the time basis vector pierces 1, 2 stacks, so this wave's frequency is 2. And the space basis vector pierces 1, 2, 3, 4 stacks, so the wave's wave number is 4. The wave's speed is just frequency over wave number, which is 2 over 4, or 1/2 meters per second. This is all according to Einstein. The ET and EX basis lets us measure spacetime from Einstein's frame of reference. But what if we looked from the frame of reference of this car, traveling in the positive x direction relative to Einstein, with a speed of v. How would the car measure this wave? All we need to do is measure this wave again using the car's spacetime basis, et tilde and ex tilde. Et tilde just points along the direction of the car's world line, and ex tilde is the exact same as ex. The car's time basis vector pierces 1, 2, 3, 4 stacks. So the wave's density in time, or its frequency, is 4, according to the car. And the car's space basis vector also pierces 4 stacks. So the wave's density in space, or wave number, is 4. The wave's speed, according to the car, is frequency over wave number, which is 4 divided by 4, or 1 meter per second. So we've seen that the wave's frequency and speed change depending on the observer. Since the car is running towards the wave's source, the wave appears to have a larger frequency and a larger speed, according to the car. We worked this out by drawing pictures and counting the number of covector stacks pierced by a spacetime basis. But we can also figure this out using algebra. Recall the Galilean transformation of the spacetime basis that we learned in Relativity 103. The car's time basis vector equals Einstein's time basis vector plus the car's velocity times Einstein's x basis vector. And the car's x basis vector is exactly equal to Einstein's x basis vector. If we want to know how many wave stacks the car's et tilde basis vector pierces, we can just substitute this formula for et tilde. And by the fundamental Covector laws, we can move addition and scaling outside the covector. So we now have a formula to get the frequency of the wave in the car's frame. It's just the frequency measured by Einstein plus the speed of the car according to Einstein times the wave number according to Einstein. We can also get a similar formula for the wave number conversion measured from the car's perspective. Notice how these formulas for converting frequency and wave number to the car's frame look very similar to the formulas for converting to the car's basis vectors. This is because Covector components are covariant, and they transform in the exact same way as basis vectors. If we remember the formula for a wave's speed, we get that Einstein's wave number equals Einstein's frequency divided by Einstein's wave speed. If we sub this in, this results in the Doppler shift formula you might see in school textbooks. And if we plug in the values for the wave frequency, wave speed, and car speed according to Einstein, we get that the car measures a frequency of 4 Hz, as expected. So what we just covered was the Doppler effect in Galilean relativity, which used the Galilean transformation of the basis vectors. Now let's look at the Doppler effect in special relativity, which uses the Lorentz transformation of spacetime basis vectors. Recall that beta is just the fraction of the speed of light, v over c, and gamma is just 1 over the square root of 1 minus beta squared. If you'll recall, in special relativity, we usually measure time in meters by multiplying the time, measured with seconds, by the speed of light c. This lets us treat time and space on equal footing because they are both measured in meters. From the point of view of an inertial frame, wave peaks for a light beam on a space-time diagram will always travel at 45 degrees, which represents the speed of light. This means that for a light wave, the speed of light c is always equal to light's frequency divided by its wave number. In other words, f over c equals kappa x for a light wave. For convenience, we will denote f over c by kappa t, and we call this quantity the time wave number. While frequency f is measured in hertz, or reciprocal seconds, the time wave number kappa t is measured in reciprocal meters, just like the wave number in the x direction, kappa x. This basically puts frequency in time and wave number in space on equal footing, because they are both measured in reciprocal meters. Let's say that Einstein measures a light wave where the density in time, or the time wave number kappa t is 2. For light beams with speed c, kappa t and kappa x are always equal to each other, if we assume that the wave is not moving in the y and z directions. So this means that the density in space, kappa x, is also 2 in Einstein's frame. But what would the time and space wave numbers be for the wave measured in the car's frame, if the car is moving towards the wave source at 1/2 the speed of light? So for the car, beta equals 1/2 and gamma equals 2 over the square root of 3. The density in time for the car is just the wave covector kappa acting on the car's time basis vector. We can sub in the basis change formula from the Lorentz transformation to write this in terms of kappa acting on the Einstein spacetime basis. We get that the car's time wave number, kappa t tilde, is Einstein's time wave number plus beta times Einstein's x wave number, all multiplied by gamma. We can get a similar formula for getting the car's x wave number, kappa x tilde. Again, the form of these transformation equations exactly matches the form of the change of basis under the Lorentz transformation, since the wave covector components are covariant. We can take this formula and turn it into a version that's more commonly seen in relativity textbooks. We can replace kappa x with kappa t since they are always equal for light waves that are not moving in the y or z directions, and then factor out kappa t. We can also replace gamma with 1 over the square root of 1 minus beta squared. The 1 plus beta on top can be rewritten as the square root of 1 plus beta times the square root of 1 plus beta. And since the bottom involves a difference of squares, we can rewrite it as the square root of 1 minus beta times the square root of 1 plus beta. We can then cancel the square root of 1 plus beta from the top and bottom. So we can see that the conversion factor between the car's time wave number and Einstein's time wave number is the square root of 1 plus beta over 1 minus beta. This also applies to the conversion between frequencies, since the time wave number is just the frequency over c. If we plug in 2 for Einstein's time wave number and 1/2 for beta, we see that the time wave number measured by the car is 2 times the square root of 3, or about 3.5, which matches our diagram. So if a frame that's standing still measures a light wave to have a frequency f, a frame running towards the light wave source will measure a higher frequency. We call this effect blue shift because the frequency shifts to the higher end of the electromagnetic spectrum, represented by blue light. Similarly, if a frame is running away from the light source, it will measure a lower frequency. We call this red shift because the frequency shifts to the lower end of the electromagnetic spectrum, represented by red light. The last thing we'll do in this video is to look at the Doppler effect for an accelerating frame. Or to be more technically correct, a frame that measures constant proper acceleration on an accelerometer that they are carrying with them. I already showed in Relativity 105a, b, and c that the world line of an observer with constant proper acceleration alpha is given by a hyperbola, with these being the equations for ct and x in the accelerating observer's Rindler coordinate system, ct tilde and x tilde, where the distance capital D is c squared over alpha. I also showed that at every point along this hyperbola, the accelerating observer has a different spacetime basis, where the time basis vector is tangent to the world line and the x basis vector is Minkowski orthogonal to it. In Relativity 105e, we showed how to change the basis in curvilinear coordinates by equating basis vectors with partial derivatives, and using multivariable chain rule to get the components of a basis vector. So from that video, we already know that the time basis vector in Rindler coordinates looks like this. So to get the time wave number that the Rindler observer measures, we just apply kappa to the Rindler time basis vector and replace it with this formula. So we get that the Rindler's time wave number equals x tilde over d times Cauchy times Einstein's time wave number plus x tilde over d times sinh times Einstein's x wave number. Since kappa x equals kappa t, we can factor out kappa t to the front. Then we can replace Cauchy and sinh with their exponential representations, where Cauchy is 1/2 times the sum of a positive and negative exponential, and sinh is 1/2 times the subtraction of a positive and negative exponential. The negative exponentials cancel, and we're left with the conversion factor between Rindler and Einstein's time wave numbers, depending on both time and space, with this exponential. In the case of Rindler's hyperbolic world line, he has a constant x tilde coordinate of d. So d over d just goes to 1, and we find that the frequency conversion only depends on time. We find that at very negative times, far in the past, Rindler sees a frequency of almost 0, because he is running away from the source of the wave very fast. Then at time equals 0, the conversion factor is just 1. This means that Rindler sees the same frequency as Einstein because they are both momentarily stationary with respect to each other at this one instant in time. Then at very positive times, far into the future, Rindler sees a frequency that approaches infinity, because he is running towards the source of the wave very fast. So an observer accelerating towards a light source will observe continuous blue shift, where the light wave's frequency gets higher and higher. And an observer accelerating away from a light source will observe continuous redshift, where the light wave's frequency gets lower and lower. So to summarize the geometrical interpretation of the Doppler effect, we can think of a traveling wave as a covector stack in spacetime. The density of the stack in the time direction gives us the time wave number, which is the frequency over the speed of light. And the density of the stack in the x direction gives us the x wave number. These give the components of the frequency wave number covector, also called the wave covector. Technically speaking, we can also add the y and z wave numbers to get a full four-dimensional space-time wave covector. To find out how different reference frames measure the frequency and wave number of the wave, we just measure the densities of the wave covector using the space-time basis for that reference frame. Because the wave covector components are covariant, they transform in the exact same way that basis vectors do. In Galilean relativity, this gives us the standard Galilean Doppler effect formula. In special relativity with inertial frames, this gives us the relativistic Doppler effect for light waves. And in special relativity with accelerating frames, we can see that light has continuous blue shift or redshift over time, depending on whether the observer is accelerating toward or away from the light source.